Here we're going to go ahead and look through section 3 in chapter 3. And now we're going to be really dealing with some quadratic functions. And we're going to deal with these quadratic functions for the next several sections. But our learning targets for today, we're going to graph the quadratic functions using transformations. And hopefully you've seen these transformations before. We're going to be using A, H, and K. Then we're going to look at the vertex and axis of symmetry of a quadratic function. We're going to look at how we can find that from a graph and from the equation. So we're going to graph these quadratics using the vertex, the axis, and the intercepts. Once we're given a vertex and a point, we can find our quadratic function, and then we're going to find the maximum or minimum. And again, when we're finding the maximum or minimum of these quadratic functions, that's the same thing as finding the vertex. Okay? So here's our standard form of a quadratic function. So I have f of x equals ax squared plus bx plus c. So a cannot equal 0, so I know this is a quadratic because I have that exponent of 2 right there. Okay, so when I'm dealing with a domain, and remember that domain is my x values, and domain is x values, range is y values. My domain for a quadratic function is always going to be all real numbers. And remember our quadratic function looks kind of like a U. It can also be an upside down U. So you see it will go on and on in both directions in the x for infinity, so that's why our domain will be all real numbers. We'll talk about what the range looks like as we get into a few more examples. So here's just a table of values that we're going to use in this first example, and we're looking at the price per calculator and the number of calculators purchased. So this is some information coming from TI, Texas Instruments, on just some of the money and how they sell their calculators. Okay, so my relationship between the number of calculators I sell and the price is given by this linear equation. And we can find that by using these points and finding the line between them. So here's my linear equation. So I have 21,000 minus 150p, and p is that per calculator price. Okay, so then I know that I'm looking at revenue. Okay, so revenue is how much money I can make from it. So my revenue is equal to the selling price times the number of units sold. Okay, so I have my revenue is the price times the number of units. Well, I can replace this because I know that from above, my x, my number of units, was 21,000 minus 150p. So I go ahead and substitute that in, and then I can distribute this p value and rewrite this in standard form. So standard form really just means that I put the variable with the highest exponent first, and then I decrease the order of my variables. So I go ahead and do that. So this is the equation that we're going to be looking at. And generally we're going to be looking to maximize or minimize revenues, and we're really going to talk about that in our next section. But we can go ahead and graph this and see what it looks like. So here's the graph of this negative 150p squared plus 21,000. So we can take this information and look at it. So my domain here, we talked briefly on the when we looked at learning targets that our domain was all real numbers. When I'm dealing with an actual word problem, a real life problem, I have to restrict my domain. So my domain for this case falls between 0 and 140. Okay, so 0 is the smallest that my domain, and domain is kind of my x values, and 140 is the largest. I know that it can't go below 0 because I cannot have a negative cost. Right? So this is where we also can look at our labels, and that helps us a lot. So my price per calculator, I cannot have a price that's less than 0. But also based on my graph, I cannot have a price that's 1 over 140. Okay? So I can take that into account as well when I'm dealing with domain and range. So often we also model when we're throwing things or when cannons fire. This is also modeled by a parabola, and we'll really get into this soon. So now we're going to be using some of those transformations. Okay? So here's our first transformation. We start with our parent function, and our parent function is f of x equals x squared. So from here, we're going to be doing things to it. So you'll notice down here, I've multiplied that x squared by a 3, and my graph has become taller and skinnier. This is our a value. This is our vertical stretch or shrink. So when this value is greater than 0, I have a stretch. When this is a fraction, right? So here's my a value. This is what we call a vertical shrink. It gets shorter and fatter. So what happens if I have a negative sign here? Well, that negative flips my graph over the x-axis. But again, you'll see the same values. The negative just flips it. This 3 will still make it taller and skinnier than it was before, and this fraction will make it kind of shorter and fatter. So this value, this negative, will affect the range. So for these equations, remember, range is my y values. So here I would say that y is less than or equal to 0 for my range. And I know that it's less than because it's going down from my 0. Okay? So when we're looking at the graph of a quadratic function, I see the axis of symmetry. And when I have that axis of symmetry, that's where I can fold the graph and it looks the same. So I have my vertex, which is where the direction changes. So my vertex can either be at the lowest point, which is the minimum, or it can be at the highest point, which would be the maximum. And we will find both of those here pretty soon. Okay? So again, what we saw on that last page, that if a, that value in front of my x squared term, if a is greater than 0, it's going to be up, opening up. And if a is less than 0, it opens down. The really cool thing is that the a value will look the same in all different forms of the equation. So we're going to look at several forms of this. Just know that a is the number with the x squared. Okay? So here we're going to be using some transformations to graph this function. So I've got 2x squared plus 8x plus 5, and then I have to find the vertex and the axis of symmetry. But we're going to go ahead and graph it first. Okay? So the first thing we want to do, and we will get to an easier way, we just have to walk through how we get there. So the first thing we do is we complete the square on the right side. Okay? So here's my original equation. I've got my 2x squared plus 8x plus 5, and then I complete the square. Okay? So I go ahead and I factor out a 2 from my first two terms, because to complete the square I really need this value to be a 1 in front of my x squared. So I can factor out that 2. Don't forget your parentheses. Now I complete the square inside my parentheses. Okay? So in order to do that, I take this b term, the term with just my x, and I divide it by 2 and I square it. So when I divide it by 2 and square it, it's 4 divided by 2 is 2, 2 squared is 4, so that's where this 4 comes from. You may be wondering where this negative 8 comes from. Well, if I add this 4 in here, it's really like me adding 8, because if I distribute this 2, I've really added 8. So to mathematically be correct, I have to undo what I just did, so I have the same problem. So I go ahead and subtract that 8 as well. Okay, so then I can actually go through and simplify, right? So I know that this now can become my factor. So again, I take this and divide it by 2, and that's where I come up with this. I've simplified and just combined these terms. So now I have a new form. Okay, so this is actually what we call vertex form. So on the beginning, we looked at what's standard form. This is what we call vertex form. Okay, so I know here's my a value, right? My a value is positive, so I know it's going to open up, which is right here. It has its vertex, which we know is going to be a minimum because it opens up at -2, -3, and the axis of symmetry is the line x equals -2. When we're finding the axis of symmetry, we always go with the x value of our vertex. That's how we can always find the axis of symmetry, so we don't have to find something new. Okay, so now let's look at the graph a little bit. Okay, so here's the parent function, and we always want to start with our parent function of y equals x squared. So when I multiply that 2 in front, it makes it taller and skinnier, so it's that stretch. This plus 2 shifts my whole graph to the left 2 units, and then this -3 shifts it down 3. Okay. So here is just some what we're looking at, and they came across this. This is from the quadratic formula. You don't really need to know a lot of this. Let me explain the really important parts. Is this right here. This is vertex form. And you need to know vertex form. And here's what you need to know about vertex form. The big important things, it's always x minus h. X minus h. Don't forget that. Okay, so what this means. So A is my vertical stretch. H is going to be my horizontal translation. So that tells me if it's going to go back and forth at all, right or left. Okay, so if h is positive, so I'll have like x minus 2, then I'm going to go to the right. So we kind of go the opposite direction that we think we're going to go. And then k is going to be my vertical translation. So that tells me if I go up or down. So we'll look at that too. So this k value out here tells me up or down. Okay, so now we're going to be identifying the vertex and the axis of symmetry of some of these functions. Okay, so the easiest way is if I don't have my equation in vertex form, have it in standard form, I can go ahead and use this to help me find the vertex. Okay, so I always take a negative b over 2a. So again, negative b over 2a, negative b over 2a, negative b over 2a. That's how we will find the x value of our vertex. Again, with this a value, if a is greater than 0, it's going to open up, and if a is less than 0, it opens down. Okay, so now we're going to actually find this vertex. So I'm asked, without graphing, find the vertex. So first of all, I want to figure out, does this open up or down? And I see that I have a negative here, so I know it's going to open down, so I'm going to have a maximum point. Okay, so to find the vertex, I have a negative b over 2a. Well, I know my values go a, b, c, and I need to always make sure that my equation is written in standard form first. So I have all of my terms on one side, and my variables have a decreasing exponent. So I take a negative b, which was 6, over 2 times a, which is a negative 3. So I have negative 6 divided by negative 6, so my x value of my vertex is 1. So now I go ahead and take that 1, and I replace it everywhere, negative 3. Everywhere there was an x in my original equation, I replace it with that 1 that I found. And when I replace things and substitute, I always include my parentheses. So here I have 1 squared, which is 2, times negative 3 is a negative 3. I'm sorry, 1 squared is 1, times negative 3 is negative 3, plus 6 times 1 is 6, plus 1. Negative 3 plus 6 is 3, plus 1 is 4. So the y value of my vertex is 4. So I've gone ahead and found both the x and y point. We always want to start with this negative b over 2a, and then we plug that into our equation to find the y value that we need. So now that we've found the axis of symmetry and the vertex, we're going to go ahead and graph our quadratics. The other thing we're really going to be looking at is our x-intercepts here. So x-intercepts are where my graph crosses the x-axis. And in order to find that, we can use the discriminant. Okay, the discriminant is this b squared minus 4ac. So if you remember the quadratic formula, this is the stuff that's under the radical sign. Okay, that's the important part. So if I take my b squared minus 4ac and it's greater than 0, it tells me I have 2 intercepts. Okay, so I will have 2 solutions. So if my discriminant here equals exactly 0, then I know I have 1 intercept. So that's my vertex. And if my discriminant is less than 0, I have no intercepts, which means it doesn't actually cross the x-axis. So think about that, right? I can cross the axis in 2 places, kind of like this green one. I can touch the axis at one place, where my vertex is, or I can have just a parabola down here that never touches my x-axis. And this is the easiest way we can find those things. Okay, so again, here's kind of the graph of what we were just looking at. So I can cross it twice, I can touch it once, or I don't have to touch it at all. And this will tell me my x-intercepts. So we're going to use the same quadratic that we've looked at before and actually start graphing it now. So I want to find my intercepts. We found the vertex, I want to find the intercepts. Then we can look at the domain and range of this equation and then figure out where it's increasing and decreasing. Okay, so we found the vertex to be 1, 4. We know the axis of symmetry is going to be x equals 1 because it's always this value here. The next easiest point to find is my y-intercept. And we find the y-intercept when we set x equal to 0. So when I set x equal to 0 in my equation, which was negative 3x squared plus 6x plus 1. When I set x equal to 0, this term becomes 0 and this term becomes 0, so my y-intercept is at 1. So that's another easy point that I can plot. So now I need to find the x-intercepts. And I find the x-intercepts is where I set y equal to 0. Okay. So now here's what I have. So I've got my negative 3x squared plus 6x plus 1 equals 0. I have my a, b, and I c. And I go ahead and I look at my discriminant, which is b squared minus 4ac. So I just plug in those a, b, and c that I found, and I see that it's greater than 0. So I know I'm going to have 2 solutions. Then I can either factor it, I can complete the square, or I can use quadratic formula. In reality, your quadratic formula is going to be the easiest way to find those intercepts. So I use the quadratic formula, which is negative b plus or minus, right? the square root of b squared minus 4acl over 2a. So I plug in the information. So here's where they put the minus, right? They write it out twice. You can really do everything kind of once. And since we were actually graphing, we can go ahead and use our calculator to simplify that because then I can actually plot those points. So my x-intercepts, where it crosses the x-axis, are at about approximately a negative 0.15 and 2.15. So now I can use the 4 points that I have to graph my equation, right? And I have my vertex, I had the y-intercept, and the 2 x-intercepts. You'll see here I have this other point. I used this other point because I'm using my axis of symmetry. So I knew here if I went over 1 and down 3, I had a point. So the same thing can happen on the right side. So if I go over 1 and down 3, I have a point. Okay, so that's another way I can just plot another point. So my domain for this one is my all real numbers, right? So domain is x. So based on the graph, my range is going to be y, because range is always y, is less than or equal to, because we're going down, 4. That's the highest point that I see. And I can also write that in interval notation. Okay, so then I can also look at where my function is increasing. And we want to see increasing and decreasing based on like if you were reading it like a book. So starting from left to right. So from here to my vertex, it's increasing. And then from my vertex continuing on, it is decreasing. We never want to include that vertex point in our interval notation because it's neither increasing nor decreasing. It's where the direction changes. So I'm increasing from negative infinity to 1, and I'm decreasing from 1 to infinity. So here's our next example. We're going to be graphing x squared minus 6x plus 9. And first we have to figure out, does this open up or down? I need to find the vertex, my axis of symmetry, my y-intercept, and my x-intercepts, if there are any. Then I can figure out the domain and range and where it's increasing or decreasing. So the first thing I notice is that this a value is positive, so I know it's going to open up. Okay, so now let's find its vertex. So I know to find the vertex, I have negative b over 2a. So I go ahead and plug those in. So my b value here is this negative 6 over 2 times a, which is 1. Negative times a negative is a positive. So my x value is 3. So this also tells me my axis of symmetry is x equals 3. I can plug this in now. So I've got 3 squared minus 6 times 3 plus 9. 3 times 3 is 9 minus 6 times 3 is 18 plus 9 is 0. So my vertex is going to be at 3, 0. So I could find my y-intercepts and my x-intercepts. Remember that the x-intercept is where my y value equals 0. So I've already found my only y-intercept here. Or I'm sorry, my x-intercept. So let's go ahead and find the y-intercept. So I can go ahead and plug in 0, and that gets rid of these two terms. So my y-intercept, when my x is 0, is at 9. So now I have these points that I can plot and come up with my graph. So here is our vertex. Here is that y-intercept. And just like we did on that last example, I can find this third point over here by knowing if I go over to the left 3, I can go up 9. So if I go to the right 3, I can go up 9. So I can find that as well. Okay. So I can also see that my function is decreasing from a negative infinity to 3, and it is increasing from 3 to positive infinity. My domain here would be all real numbers. My range would be y is greater than or equal to, because it's opening up, and the lowest point is when y is 0. So that would be the range for this function. Okay. So again, here's another example that we can follow exactly what we just did. So first thing I notice is I have this a value that's positive, so it's going to open up. I can find the vertex by doing my negative b over 2a. So I've got a negative 1 divided by 2 times 2. So it's a negative 1/4. And I can plug that back into my x and find the y value. I can find my y-intercept by making my x is 0. So my y-intercept would be 0, 1. My x-intercepts I can find by setting y equal to 0. So here's what this looks like. So here you'll see we don't have any x-intercepts. My graph never touches the x-axis, and that will happen sometimes. But again, I can graph this using my vertex that we found with this negative 1/4, and when we plug it back in, we'll get 7/8. My interception point, my y-intercept, and then we can use the axis of symmetry to kind of fold this point over to find a new point. So now we're going to be given a vertex and one other point of our quadratic and asked to write the equation. Okay? So here we're going to use vertex form. So generally when you're given the vertex, we want to use vertex form. So now let's just see what we can do. So determine the quadratic function whose vertex is 1, -5, and whose y-intercept is -3. So the first thing we want to do is remember our vertex form. Okay, in our vertex form, y equals a times x minus h squared plus k. Well, let's plug in the things we know. We know that the vertex is h comma k. This is always going to be our vertex. And then we can use this other y-intercept point. So a y-intercept is when x is 0, my y is -3. So we're going to use that other point. So first, let's plug in our vertex, minus h, and the h was 1 squared, plus k was a -5. Well, now I'm going to go ahead and use this x and y as my other point. So I've got -3 equals a times 0 minus 1 squared plus a -5. Well, now I'm left with one variable, so I can continue to solve this. So I have -3 equals a -1 squared is 1, which gives me a minus 5. So then I add 5 to both sides, so I get a equals 2. So now I can write my final equation back up here. So I have y equals 2 times x minus 1 squared minus 5. This is the final equation using the vertex and another point. Okay, and this is exactly what we just did. We can also write it out in standard form. So if you go ahead and simplify this into standard form, either way, I will accept vertex form as well. So this is what it looks like when we graph that one. So we can graph it using that vertex form. Actually makes it much easier for us too. Okay. So now we're going to look at the maximum minimum, and we've been doing this before. Okay. So determine whether it has a maximum or minimum, and then find the maximum or minimum. So we really want to first find the vertex here. So I notice that this a value is positive, so my graph will open up, so I will have a minimum value here. So now let's find that minimum value. So to do that, I find my vertex, negative b over 2a. So I have a negative of a -4 all over 2 times a. So my x value of my vertex is going to be 4 over 2, which gives me 2. This is not the actual maximum or minimum. This is where it happens. So to find the minimum, I plug that 2 back into my original equation, and I find the value here. The y value will be my minimum. So 2 squared is 4, minus 4 times 2 is 8, minus 5. So 4 minus 8 is -4, minus 5 is a -9. So my minimum value for this function would be -9. So again, all I did first was determine, does this graph open up or down? So that will tell me if I have a maximum or a minimum. And then I find the y value of my vertex, which will give me that maximum or minimum. So now let's look back at our learning targets, because we made it through all of them. So first we graphed a quadratic using transformations. We found the vertex and axis of symmetry. Then we graphed a quadratic using that vertex and axis of symmetry. We were able to write a function when I had the vertex and one other point. And then we looked at the maximum or minimum of these values. Okay, so now that we've gone through all of these targets, go ahead and work on your homework for this section.